Okay, paths and cycles. So paths and cycles are a concept in our graph theory or network sort of topic. You need to be very careful about the terminology in this topic. So we've got walks, we've got trails, we've got paths, and they all sound like similar things, but they mean something very different. So in your exam questions, you need to read very carefully to see which one you're doing, and basically it'll dictate whether or not you can repeat vertices and edges and those sorts of things. So a walk is basically a movement between any connected vertices. The graph must be connected. And in a walk, you can repeat anything. So you can think of that as a kind of a very random movement. You can go anywhere you like. You can repeat anything you like. The only rules are no bush bashing or flying. So there must be an edge between the vertices in order for you to get from one vertex to the other. An open walk is one where you start at one end and you finish at a different vertex. So a closed walk is where you start and end at the same vertex. The other thing they might ask you is about the length of a walk. And the length of a walk is basically the number of edges you traversed. Be a little bit careful here. If you had a weighted graph, then obviously if they are asking for the distance between places, you'll need to take into account the distances marked on each of the edges. But if there's no distances marked, then it's just how many edges have you travelled. So here, if I said we did a walk from A to B to C to D to E, so I'm going to put my highlighter on there. So where I've gone is starting from A, I've gone from B to C to D and then to E. So that's my walk. It would be called an open walk of length 4. Now, this is actually not only a walk, but it would also qualify as a path because I haven't repeated anything, but we'll get to that. The length of it is 4 because you can see I went along 4 edges. If you didn't have the graph to look at and you just had the string of letters, then just count your movements. Don't forget there'll always be one less edge than the number of vertices. So if we looked at this particular path, I've got 1, 2, 3, 4 edges. So that's the other way that you can keep track of that. Mostly when we have a walk, we probably would have repeated something. So if I change colours here, I might have gone from, let's say, A to B, back to A, then to D, then to C, then to B, then to A, then to D, then to E, whatever. And I can repeat and do anything I like. But to count them, just keep an eye on that movement between the letters and you'll get there. Okay, just move that back for your notes later. Okay, so a path is different in that you can't repeat anything. So in a path you repeat nothing. So you can't repeat any edges and you can't repeat any vertices. So we associate this with the concept of something being Hamiltonian. We'll cover that later. But not every path will be Hamiltonian, but some of them will be. A path can also be open or closed. So an open path is one, again, where we start and end at different vertices. And a closed path is one where we start and end at the same point. If it's a closed path, then we also use the term of cycle. So in a cycle, we're going to start and end at the same point, but the important part of a cycle is that you haven't repeated anything. The length of a path equals the number of edges once again. Now a trail is basically a walk in which we can repeat the vertices but not the edges. And this concept is going to be important when we start talking about the concept of something being Eulerian or semi-Eulerian, and we'll get to that in a moment. And again, a trail can be closed or it can be open, so it would be an open trail if I'm starting and ending at different vertices, or a closed trail if I start and end at the same vertex. Now in that case it's going to be a circuit, but notice the difference between the circuit and the cycle. In the circuit you are allowed to repeat the vertices. So this brings us to Eulerian and Hamiltonian concepts. Now these are one of the most important concepts you must get your mind around for this topic. Something is Eulerian. Basically I've put two rules here. First of all, it's Eulerian if it's a connected network. And secondly, it must be traversable, which means we can travel right around that network and cover every single edge once only without repeating any edges. We can repeat the vertices, and that's why we call it a Eulerian trail and as opposed to a Eulerian path. And again, if we began and ended at the same point, then it would be a Eulerian circuit. because we can repeat the vertices, but we're going to begin and end at the same point. And we've got a little trick to find that. If you looked at a very complicated network, you can see at a glance whether or not it's going to meet the requirements to be Eulerian by counting how many odd and even vertices you have. So I always get into the habit of just circling all my odd vertices in any kind of diagram, and we're looking for no odd vertices in order for it to be Eulerian. Now, if it's an open trail, then we start and end at different points, and in that case, what we would need to be seeing is exactly 2 odd vertices. It won't work with anything else, so we need 0 odd vertices to be completely Eulerian, or exactly 2 odd vertices to be semi-Eulerian. And if that was the case, now I forgot to put that in your notes, so I'm going to add that in there now. If that was the case, then in order to traverse the network, we'd have to start at one of the odd vertices and end at the other one. So I'll add that there. So to traverse this network, start at one of the odd vertices, and they often put this in your exam. They'll ask you to come up with a route. Okay, and finish at the other odd vertex. And there'll be no other way in which you can do this without repeating an edge, which you're not allowed to do. If you're asked to show a path, then you should highlight it, but you should also list the vertices, so whatever you've done, you know, A, B, C, D, whatever, and show what you've done. Sometimes they'll also ask you for the length of a path, so in that case you'd show the distance and then show, in this case my length is 1, 2, 3, so sometimes I need to show that sort of thing, but that's more a shortest path concept, more so than a Eulerian concept, but sometimes they combine those. Now, Hamiltonian is the other concept that we need to cover. A cycle is Hamiltonian, and again I've used that word cycle so purposely because basically to be fully Hamiltonian it means I must start and end at the same point, which by definition means it's a cycle, and because I can't repeat anything in a Hamiltonian thing, it is a cycle and not a circuit. So a cycle is Hamiltonian if it is a path, so I cannot repeat any vertices or any edges. Not all paths will be Hamiltonian though. What makes a path Hamiltonian is that I must go to every single vertex once and once only, apart from the beginning vertex. Now, I don't need to travel on every single edge. So typically the context of a Hamiltonian question will be something like where I need to deliver something to every single town. So I don't need to travel on every road in every town, but I need to get to every town to drop off a parcel or do something like that. It might be often tourist questions where you're going to a famous place and you want to visit all the tourist attractions. So each vertex would represent an attraction. I want to get to every vertex, but I don't need to travel on every road in the town to get there. The Eulerian concept, again, we need to connect these concepts with where we're going to see them in questions. Generally, if I'm using a Eulerian sort of thing, I'm planning something like a rubbish service in a town where I need to travel down every single road to collect bins, or it might be a mail service where I have to go to every single house to deliver mail, and therefore I obviously want to do that without sort of wasting my time by doubling up on travelling roads twice. So often they won't tell you that you're looking for a Eulerian or Hamiltonian, but the context of the question will clue you in. Now again, we can also have a semi-Hamiltonian, so that would mean that I'm doing a path but not a cycle. So I'm starting at one vertex, ending at a different vertex. And again, I cannot repeat any vertices or any edges. If an exam question asks you for a Hamiltonian cycle, then make sure that you don't just assume it can be semi, unless they've specifically used the word path and not cycle. If they've asked for it to be Hamiltonian, it must be fully Hamiltonian. So generally, if they ask for Hamiltonian, assume it's a fully Hamiltonian that they're looking for. So let's have a look at a few graphs. Now, this is from the review section of CLUP. He's given us a series of networks, and he's asked us here whether each of the networks are traversable or not traversable. That will determine whether they're Eulerian or semi-Eulerian or neither. And he's then asked which of these are semi-Hamiltonian. And so again, I'll cover each of these. I'll look at Hamiltonian as well. So use a highlighter. You in your kit should include multiple erasable highlighters, because if you do an exam, it's going to allow you to draw around networks and undo your drawings, because if you make a mess of these diagrams, they become quite hard to mark. So for the first one, let's have a look and say, well, is it going to be traversable or not? The first thing I'm going to do is do what I was saying and look for the odd vertices. So this first vertex up here is even, there's 2 coming in. I'm just going to circle the odd ones. This next one is even. I've got 1, 2, 3, 4 vertices coming in, so it's even. Over here, 1, 2, 3, 4, it's even. In the middle I've got 4, so that's even. Over here though, I've got 3, so that one there would be odd, and another 3 here, so that would also be odd. So remembering our rule, if I've got 2 odds, it would be semi-Eulerian, it would not be fully Eulerian, and I would be able to traverse this. In order to do so, I would need to be travelling, sorry, I'm going to highlight it. In order to do this, I would need to be travelling, starting from one of the odd vertices and ending at the other. So let's have a go. So if I was here, if they wanted you to list a path, they would have labelled the vertices with an A, B, C, D. But we'll just go around and you would need to comment on that. But here we'll just do it. So here you can see I'm going to go up. Doesn't matter which way I go. There's multiple ways I could do it. You can, oopsies, that moved on me. So here I would then go here. You can see I'm repeating that vertex, but that's fine. I'm then going to come down here. I'm going to go up. Again, I'm going to repeat this vertex. And then coming down here, I've repeated a vertex again. I'm going up to the middle, repeating a vertex. That's fine, repeating a vertex. And then I'm going to end at that last one. So by using the highlighter, it makes it a bit easier for me to see that I have gone around all the edges and I don't accidentally miss an edge out. Again, in the exam, if these had letters on them, so if they had written, you know, given these titles, labels A, B, C, D, E, F, let's say, then as I went around, I would need to keep a record of where I went. So I went A, B, C, yada, 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 but actually record that so you don't lose track. It's a bit harder to see afterwards. Let's try the next one. So again, my top one has 2 coming in, so it's even. My next one here has 3, so that would be an odd. The one to the right has 3, so it's an odd. Down at the bottom, I've also got an odd. So as soon as I've exceeded those 2 odds, I automatically know that this is neither Eulerian nor semi-Eulerian. So I could tick both of those off. Pardon my dog yawning in the background. Is it Hamiltonian? Well, to be Hamiltonian is fairly easy to achieve. I just need to visit every vertex once without repeat. So let's have a look. So starting here, I can pretty much make my way around and back to the beginning. So yes, it would be Hamiltonian. I don't need to travel on every edge, but I've been around and I've begun and end at the same point. If I wanted it to be semi-Hamiltonian, I could just undo that last edge. I didn't mean to undo the whole lot, but we'll go again. So again, I could just go around and just stop one earlier, and that would then be a semi-Hamiltonian path. Let's have a look at the next one. So here I've got an even one at the top. I've got an even one here. I've got 1, 2, 3, 4, so I've got even to the right. I've got an odd one in the middle. I've got 3 coming in. I've got an odd one down here with 3 coming in. And I've got 2 there, so that's even again. So again, if I've got 2 even ones, I'm semi-Eulerian, I'm not fully Eulerian, and I could make my way around this network by starting at one of the odd ones and ending at the other. Doesn't matter which way we go. So here, if I just give this a go, it can be pretty random. I know, and I can't repeat any edges, and I haven't. I've repeated vertices, but not my edges. Okay, so let's have a look. So I'm just going to let my dog out. Sorry about that. And let's have a look at the next one. So you get the gist of these. We probably don't need to do more. If I had, let's do one more here. These are the ones people tend to miss. Okay, I don't know why, but people always miss the ones that are out on a little bridge on their own. So with a bridge, I can see that one there's odd. This one here is even because I've got the 1, 2, 3, 4. This one here is odd because I've got 3. So once again, this one would be semi-Eulerian, and if I wanted to traverse it, I'm going to start at one of those odd vertices, and I'm going to go around, and I'm going to end at the other odd vertex. Now, another thing I wanted to highlight here is this little bridge. As soon as I see a bridge, I know automatically that this is not going to be Hamiltonian. there is no way that I could go all the way around this network and start and end at the same point without having to go over this bridge twice. So if I demonstrated this to you here, take off all those. So it wouldn't matter where I began. If I'm going to go to every vertex once, as soon as I want to visit this vertex out here, as soon as I want to visit that vertex out here, I've got to repeat that edge to get back to that point. Even if I started there, to get back to it, I've got to repeat that bridge. So bridges are the one thing you can look out for when you're doing a Hamiltonian, when you're looking for a Hamiltonian, whether it's possible to do a Hamiltonian circuit. And as soon as you see a bridge, it can't be fully Hamiltonian. Could be semi-Hamiltonian though, and if I was going to achieve that, I'd probably need to start at that point at the bridge. So, well, at the point that's going to cross the bridge. So here I would come around here. Doesn't matter which way I go, but I'm going to go to every vertex once, and I don't have to come back to the beginning, so it's nice and achievable. Okay, that's probably about all we need to cover there. If you have any questions, give me a yell.